Hello everyone, and welcome to our review of the second round of the senior paper from this year. It's just a couple of days ago at the time where this is uploaded, but if you're watching this in 2024, of course it's going to be a year since then. First things first, it appears that the senior round 2 is getting hard, right? I mean, it has always been hard, but it has been getting harder in the last two iterations of 2022 and 2023. So I think it's important that we keep our targets realistic. It's not like you're going to go there thinking that it's the same as junior, I must solve 4 questions. That's not going to happen for all but maybe 1 or 2 people in a good day. So keep your targets realistic, and I'll be quite clear as we discuss this, which problems I think are appropriate for you to try and which problems you can get some partial marks and which questions are just simply very hard. Now, before we get to the rest of the questions, I want to point out what most of you are already aware of, which is that question 2 of the senior round 2 is also the last problem of the junior round 2. This is tradition that there will either be a repeated or a similar problem between junior and senior because they are at the same day at the same time. But this was not an easy problem. It's a problem that actually needs Vieta jumping. So that's not normal, and it is therefore unlike the usual junior problem. The usual junior problem that is moved over to senior is quite doable, and this one's actually quite hard. So my suggestion for all of you who are watching this is that you can also see my description from the junior video. I'm going to not go through it here to keep this video a bit shorter, but I will include a link in the description below so that you can refer to how I explained this particular problem. Additionally, the full solutions have also been uploaded and the link is also in the description below. You can view it in order to get a better understanding of how to write out your solutions to some of these problems. My focus here is on the problem solving side and the intuition, so not as much on how to write it, because how to write it will just be a bit of a boring video for me to just write down things over and over again and improve on the first draft to a second draft. So let's not try to do that here. And instead, let's get right back to question 1. Question 1 starts with ABCD being a square. I love that. ABCD is a square. E is a point, so any point on the side DC, and then you have the triangle ABE is where you will draw your 2 altitudes. I think maybe just draw it somewhere a bit lower. So this is the point that we are thinking about. We are thinking about H. We are thinking about the intersection here, H, being at a 90-degree angle when you join it to A and B. Now, the first thing that comes to mind is that I don't really want to worry too much about the 90 degrees as 90 degrees. Instead, I see that there are so many other 90 degrees that really this is more about saying that is this intersection going to lie on this circle, which in my diagram admittedly seems a bit less true, so let's try to adjust it to look a bit more like it does lie on the circle. It should, right? If you try to do some angle chasing on the basis of AHBG, AFBH, or something like that being concyclic, you have a bit of trouble. At that point, if you are in trouble, there are two resolutions. The first option is to just go for coordinate geometry straight away. Coordinate geometry is very appropriate here, seeing as it's a square. It is going to be A, B, C, D, E, very nice coordinates, and you just calculate what are F, G, and H, take a couple of gradients of AH and BH and show that they multiply to -1, and you are done. So of all the geometry questions we have had in senior, I think this is one where coordinate geometry is actually very suitable. However, that's not very interesting to talk about, so I'll just show a different option. And the other option which I'm going to show is to think very much about what makes a square a square. Sounds silly, but what makes a square is going to be all that we need to solve the rest of this question. The first thing that makes a square is, and not just a rectangle, is that all the sides are equal and you have full symmetry. And I would like to use that by drawing in the diagonals. Now I'll draw in the diagonals and say they intersect at O. And the diagonals will also form a 90-degree angle. And so therefore, if they also form a 90-degree angle, more things lie on this circle with A, F, O, G, and B. All these are already concyclic, and you just need H to be with one of them, which is already not so bad. More options is always a good thing. The other thing that makes it a square is that if I use diagonals bisecting, that's only a rhombus. A square has 90-degree angles, which means that when you bisect them, you get a lot of 45-degree angles. And since we have just placed all of these very nicely on a circle, you can do a little bit of angle chasing with those 45-degree angles to see whether they show up anywhere nice. For example, the 45 degrees show up at the vertex itself, and they show up at the vertex itself in the circle as well, which allows me to use my basic circle properties to say that I'll get an angle here that is going to be 45 degrees. So angle EFO is going to be equal to angle OBA, is 45 degrees. And of course, 45 degrees is also what EDO is. So you get a cyclic quadrilateral. This is most certainly not specific to EFDO. On the right side, you can also say that EGO is equal to OAB equals to 45 degrees is equal to ECO, which means that ECOG are also concyclic. Now, why do we want to find these other cyclic quadrilaterals? Well, apart from having no idea what else to do, we can say that in fact this is a very famous configuration. If I plug out DC and H, and I just want to focus on the location of E, F, and G. So something like that. What happens is that if you draw the circles like this, the property that we should have is that these 4 points are also concyclic. This is known as your Mickle point configuration. The explanation is not very difficult at all, but it's just useful to recognize this pattern. 2 circles give you the third one. And the reason is that, well, if I were to just look at these opposite angles, FOG is 180 minus, FOG is 360 minus the 2 other angles there, which both lie in their own respective circles. So 180 minus FOE becomes EDF. The other 180 minus GOE becomes GCE. And these two collectively are just 2 of the angles in the triangle. So it will be 180 minus the other angle, FHG. So FOGH are concyclic, which is what you want, because it means that H also lies on the circle where all the fun is happening. So H lies on that circle, HB will be indeed 90 degrees because AB is the diameter. If this makes sense to you, then great. If this feels like something that, okay, I don't think I would have such a great chance of discovering that, you also have got the coordinate geometry approach that you can take. So let's jump ahead now to question 3, which for question 3, let me try to make this as intuitive as possible. It's not easy, but it actually makes sense. Now, first things first, this is definitely a graph theory question in the sense that, well, if you even tried to draw a diagram of islands and bridges, how would you draw it? An island connected by bridges. I mean, that's a graph, so it is going to be inevitable that you will draw something like that. Now, we call this a graph just to mean that, okay, all the properties about edges, vertices, we can start thinking about. But it's naturally how you would depict this, right? N islands, N minus 1 bridges. How else do we draw that? The only basic graph theory concept you need to have is that one can travel from any island to another with N islands and N minus 1 bridges. Means that if it is connected and there is one more vertex than edge, it means that the graph is a tree, i.e. no cycles. Intuitively, this also makes sense because if you try to draw it and you waste any extra bridges, you realize that you're not going to have enough. So this is something that should make sense to you. Each time, if you start with no bridges and you just draw one at a time, you're just inviting one more new island to be connected to the rest. So you will need N minus 1 of them to all be doing useful work rather than just forming random loops here and there. So that's the first thing, right? The graph looks like a tree. Now let's experiment and think about it. So at first, a fire breaks out in one of the islands, and then every morning it spreads to all the neighboring islands, and then after that, you are able to destroy a bridge at night. Now, this means something like the following, right? You start off with, let's say this is on fire, and let's say this is connected to these 3 different islands here. And then these 3 different islands are all connected to, I'll just draw a box to mean all the other network of islands they are linked to. Essentially, if you did nothing hypothetically, it means that these 3 are now going to catch fire. However, you can do something. So obviously, it would make more sense to destroy one of these 3 bridges as compared to one of the bridges in the box, because if I cut off this entire branch, then all of these are safe. And if they're all safe, then why would it have made sense to, let's say, cut off something from inside the box? I might as well just have denied access to that entire portion itself. And so therefore, it would effectively mean that I will save one of these, whether it is the left, the middle, or the right, and then the next day, you're going to have these two portions to deal with, because my root is kind of already just, it's on fire, right? I can't do anything to save it, so it's not going to do anything anymore. Now, notice that what has happened is that you have gone from like the original thing with one thing on fire and some connected things to now two things on fire and some connected things. So the question is, what is the best one to save, right? When I put the cross there, by breaking a bridge, it means I'm saving some portion of it. Now, let me think about it, right? So there are various ways in which the rest of it in the box could look like. Now, it's possible that my box looks like this. It's possible that my box maybe looks something like this. And it's possible that my box looks something like this. Now, depending on the situation, you may choose to save a different one. But what I can say is that this one here, if let's say that there was this box, it was just only going to be like this. I would tell you that I'm not actually going to be very concerned about saving it. And the unfortunate thing about this question is that one way to solve the problem is to just let everything catch fire. So the question seems to have been set by an arsonist, because based on this question, it means that, for example, if the starting was like this case here, I could just say that I can do nothing actually, and it makes no difference, because if I did nothing and I just destroyed, well, whichever one I want. So if I destroy, let's say, this one, then everything else catches fire, and somehow that is considered to be the problem is solved. The fire has stopped spreading because everything has caught fire. It's a bit unfortunate, but that is what the question says. So my concern, therefore, is going to be actually more of, let's say, this kind of scenario. I need to stop it, because otherwise you'll just go on and you'll go on and you will go on. So the worst case scenario is going to be a long chain. Well, not really, right? The worst case scenario is not a long chain, because I can just cut it off and then the rest are going to be fine. But nonetheless, my observation is that I can ignore small trees. Because if the tree is going to catch fire anyway, I just let it burn, rather than keep on trying to save that tree when it is going to burn in a day or be saved in a day. I can just ignore it and deal with the others that are potentially going to get much bigger. Based on that logic, here's how I would think about the worst case scenario. Now, the worst case scenario would be something like this. Just a few lines. Now, this is a problem because it means that unless I do something, it will keep burning. It's not going to be something I can ignore, and within a couple of days, everything has burned up and that is it. So because of that, if let's say I had this scenario, let's say that now I had this scenario, I broke off this bridge, then after that, now these three are on fire. Then I say, okay, I broke off this bridge. There's still enough to burn. Then I break off this bridge, And this one, there's still something to burn. So I have to break off this bridge. And so that will cost me 4 turns because I need to keep on breaking bridges over and over again. And so the worst case would be that I have got n chains of n plus 1, which is the one that's originally in fire. It will need n bridges to be destroyed. That's my intuition. And so n chains of n and the one root needs n bridges to be destroyed means that, let's say here, if I get 17, it needs 4. If I had 3 chains of 3 plus 1, so if it's 10, I need 3. Now everything from 10 onwards, obviously I will need 3 if I just extended the last chain a bit longer. So you can't do better than 3 for 10 to 16. But my conjecture is going to be that the maximum x would be square root of n squared minus 1, because there's n islands, right? So square root of, well, not n squared minus 1, square root of n minus 1 rather. So if it's 17, square root n minus 1 will be 4. If 10, square root of n minus 1 is 3, that's correct. If it's anything in between 10 to 17, I want it to also follow the 10, and so I will have this floor square root n minus 1. Now, it's obvious that you cannot do better than n bridges if you have got n chains of n, because you have to at some point address each chain, otherwise it will just go on n days anyway. So if you don't do anything and you just keep on breaking, let's say, useless bridges, it will really take n days. If you did something useful, it still takes n days. Now, how do I prove that something like this is actually going to be the worst case and everything else is fine? So my question is basically something like this, right? I know that 101, it might take 10 bridges, but 100 should take 9 bridges. So are 9 bridges, or rather destroying 9 bridges, enough always for 100 islands? Now this is literally the numerical example I was thinking about when solving this question. Is 9 bridges enough for 100 islands? And then my reasoning was that probably, because let's say that I am currently in this situation, right, where I'm deciding which one to break off, which I just call these trees, let's say T1, T2 to TK. Now I'm deciding which of these I'm going to save. Well, so 9 bridges means 9 days. If any of these have at most 9 islands, sorry, I'm just going to ignore you and just let all your islands burn up. Very unfortunate, but that means that the worst case scenario, if anything has less than 9 islands, I can ignore it, right? So it will only be a problem if some of them have, or rather if all of them have at least 10 islands. Now if I assume that they all have at least 10 islands, then they can't all be 10, right? Because in total, there's 99. So some island has 11. Now, I think about the extreme case of, let's say, I have got 9 sets of 11. Now, what happens after you have 9 sets of 11? Is that you chop off one of them, you have got 8 sets of 11. And if you have 8 sets of 11, then 8 sets of 11, each of them, the tip is on fire. So you've got 80 not on fire. And I want to do that in 8 bridges. Now what I want to realize is that that's actually the smaller case, right? 80 not on fire is, if I had 1 on fire, that is 81 islands with 1 on fire. And that tells me that I can actually do some sort of induction. And so I'm going to improve this and say that the maximum x, not just at the start, but at any point in time, is going to be the square root of the number of accessible islands. So if the island is far, far away, we don't count it, but the number of accessible islands not on fire. That's going to be my conjecture. Now, based on this conjecture, if it's true, then 80 islands not on fire would only need 8. Now, I'm going to call this thing not just a conjecture anymore. This will be my induction hypothesis. So by the induction hypothesis, 8 more will be enough in this situation. So the last thing I need to think is that whether I was just being very nice to myself, or is it actually possible to have something that is much worse? Surprisingly, the answer is no. Can't be much worse, because if your islands have if your tree has a lot of islands, we just totally can cut it off, and that will reduce the number a lot. If they are very evenly spread, we get something like what we just described. So in general, what I would do is just save the largest tree of islands. So you save the largest tree of islands, and the largest tree will at least have, in my case, ceiling of 99 over k. So your accessible and not on fire, you're going to start off with 99. K minus 1 of the new ones on fire are taken away from this count. And then ceiling 99 over k is also taken away from this count. So 100 minus k minus 99 over k by AMGM, you're going to have less than 81. And since you're going to have less than 81, this ensures very nicely that our induction hypothesis guarantees that 8 more are going to be enough also applies to here. Now I've just picked a specific number, so the actual proof is going to include more variable names, look a bit more ugly, but intuition is going to just be exactly this for everything else. Question 4. Question 4 is actually a bit easier, I believe, because what you need to do here is maybe less unusual. It's technical though, so if you haven't seen it before, then it's going to be a bit tricky. We can start with the usual few small examples if we just want to see what's going on. So n equals to 1 gives you 1 plus 1 is 2. So m is 1. N is 2 gives you 2 plus 2 equals to 4. That's m equals to 2. N equals to 3 gives you 6 plus 4 is 10. That does not work. N equals to 4. 24 plus 8 is 32. Well, that is 2 to the power of 5. So we have another one. And so far, I think we are seeing, okay, 3 of them worked. But it feels a bit coincidental, right? It doesn't feel like you should be able to keep on landing on a power of 2 every single time when you just add a factorial and a power of 2. What reason is there? So a lot of these are very clearly not powers of 2. But you might ask, well, how is it so clearly? I mean, do I need to calculate this? So the answer is no. We would check it by just trying to factor out as many 2's as we can until if it stops means that it's not a power of 2. If you try to do that, you notice something interesting, which is that, let's say 120 and 16. 120 is 8 times 15. It doesn't have 16 inside. 720 would be 16 times 45. It doesn't have 32 inside. Meaning that if you actually factored it, it will be 8 times 15 plus 2. This will be 16 times 45 plus 2. And that's a problem. It's a problem because if n factorial has less than n minus 1 2's, we can factorize out and end up with 2 to the, let's say, something times odd plus even, right? Which is not going to look like a power of 2 at all. So my first question is, when will you have enough 2's? If you persisted a little bit, here still no. But the next one would be yes. And it's not hard to see why the next one is yes, because you basically multiply in 8 into the factorial. So suddenly, from 16, you jumped up to 128. Does this work? Well, 316 is still not a power of 2, so 8 doesn't work in this case. But it only is going to have 2 squared times 79. Nonetheless, we got the 128. So I also see that 8 is a power of 2 itself. Now let's do something quick, right? And so what I'm going to do is just to use a notation. Let v2 of x be the highest k such that 2 to the k divides x. This is a notation just to mean how many 2's are there. I'm sure you have seen before how we would count 2's, right? Let's say if I took something like 16 factorial, you would say that 16 there are 8 even numbers, and then 4 multiples of 4, 2 multiples of 8, and 16 itself. That gives you 15. So 16 factorial has 15 2's inside. Now, in fact, there is a general formula, and the general formula is that if I wanted to get the thing for n factorial, again, you've seen this before multiple times, but the more usable version of this would be just to say it's n minus s2 of n, and s2 of n is the number of ones when n is written in binary. Now this is known as your Legendre's formula, which is actually Both of them are known as Legendre's formula. We're just more familiar with the first one. We don't need to know too much about binary to know that S2n, which is n written in binary, only has a 1 if it is 100, 1000 in binary, if n is a power of 2. And otherwise, it would have more than 1, 1. And therefore, nice things happen. Nice things happen, which is that if n is not a power of 2, then we get the above mentioned contradiction. It is less than n minus 1, which means that the whole left hand side, you get less than n minus 1 of it. And m is just counting how many 2's there are. So if m is less than n minus 1, then obviously 2 to the m is less than 2 to the n minus 1, which is going to not work. So we just need to come back and think about what is happening for the powers of 2, because n equals to 1, 2, 4 worked. N equals to 8 didn't work, and I haven't actually calculated 16, so I think I should try to think about 16. Will 16 be a solution? If yes, I will learn something. If no, I will learn something. So let's think about 16. Now, V2 of 16 factorial is 15. So therefore, if I took 16 factorial plus 2 to the power of 15, I should be able to factor out 2 to the power of 15 and have, well, something here which is going to correspond to 16 factorial over 2 to the 15. That should be a whole number. An easier way to think about it is that 2 to the power of 15 is taking out all the 2's from 16 factorials, which means taking out all the 2's from the numbers from 1 to 16. So your odd numbers are going to just be themselves. 1, 3, 5, 7, 9, 11, 13, 15. Then your even numbers, you divide by 2, they look like just 1, 2, 3. Wait, hang on. The 2 doesn't even survive as a 2. So if let's say I want to say what happened to 2, 4, 6, 8, then 12, 14, and 16, these guys here, which only have 1, 2, become 1, 3, 5, 7. And then after that, these guys with 2 2's become 1 and 3. And then the 8 and 16 just become 1 and 1 again. And what I would like to do is just to kind of, I don't believe it can be so coincidental that this thing here is a power of 2 minus 1. That's hard to believe, right? How can there be a power of 2 minus 1? So to test that, I'm going to just use various modulos. So if I try mod 4, if mod 4, 1 and 3 gives you negative 1. So each pair here becomes minus 1 mod 4. Oh no, there's 7 of them. So 7 of them means minus 1 mod 4. Okay, so it is 0 mod 4. Okay, so I can't use mod 4 as an explanation. Let's try mod 8 then. Because earlier on, it was 2 squared times 79, right? So it was 0 mod 4, but how about mod 8? Now, for mod 8, to save us a bit of time, we just recognize that 4 numbers in a row would be 1, 3 minus 1, which is 1 mod 8. So this, and this are all going to be 1 mod 8, but there's 1 times 3. So it is 1 cube and then 3 and then 1 and 1 again. It is only going to be 3 mod 8. Okay, plus 1, right? So 4 mod 8. And 4 mod 8 is only going to have 2 2's inside. Now, the fact that it only has 2 2's inside means that how can this be a power of 2? This is a power of 2 only if the thing in the bracket is literally 4. So it has to literally be that k factorial, you divide off by the 2 to the power n minus 1. Sorry, not k factorial, n factorial. This thing here has to be 3 itself. And I think it's very obvious that n factorial is 3 times 2 to the n minus 1. This doesn't work if n is anything more than 5, because 5 factorial has 5 inside, and therefore dividing would not give you 3. So this tells us that the only powers of 2 that work would be n equals to 1, 2, or 4. And if we were to just go back up to the top, we see that indeed those did work, and everything else below doesn't work. So this is a pretty technical number theory question, but intuition is really about just counting 2's for the entire question. Sort of an extremely upgraded version of our round 1 questions of counting 2's and 5's when looking at the number of zeros at the back of a factorial. Now, lastly, I'm going to look at question 5, which is very complicated sounding but actually surprisingly simple. I have to admit I read it wrongly about 3 times, so read it very carefully. You have 4 hours, so you should read every question. You don't know which is the easy one. Trust me. We can't tell. I would say that in this paper, you could argue that question 3 is the most difficult, just from a conceptual perspective. Question 2 needs Vieta jumping. Question 4 needs Tetler-Jonder's formula. Question 1 and question 5 don't really need anything complicated. So funnily enough, is this one of the easier ones? Possibly. So read it bit by bit. So 2,000 different colors for your 20,000 by 20,000 square grid. Of course, I can't draw that. 2 squares are neighbors if they share a vertex. So this means that diagonal and orthogonal both count. Right? Sharing a vertex includes sharing an edge. A path is a sequence of squares such that 2 successive squares are neighbors. So that is what I would think a path means. So it could look something like this is a path. Basically just connected, right? When you have got a bunch of connected squares, we can form a path. Mark k of the squares, and this is the key thing in the question. Mark k of the squares, find the maximum value of k. Right, so what do I have about this marking? 1. For each unmarked square x, there is exactly 1 marked square y of the same color, so that x and y are connected by a path of squares of the same color. Okay, let's try to understand that. So I've got x here. There is a path to y. So I'm going to just not draw a grid, I'll just draw like a visualization of it where y is marked and this is not marked. So on this path, obviously nothing else can be marked, right? Because if anything else is marked, then x could also reach there. So all of these have to be unmarked. Now, all of these then are also connected to the marked square y. So if let's say that these also connect to some other squares, they also have to be unmarked. Now, that means that regardless of how my region looks, it may be very weird shaped, I know that the region can only have one marked square if I just were to, cluster the same color into a region. So each region has exactly one marked square. It still needs to have one. Which of course means that marks are roughly the same as regions. So maximum number of k means how many different regions can you have? That's the first question. First statement. Second statement, for any two marked squares of the same color, any path connecting them must pass through squares of all the colors. So how many would there be? Now I'm thinking of the silliest example, my construction. And my construction is just going to be have a column of color 1, a column of color 2, a column of color 3, and so on. And then after you just keep repeating. So a column of 2000 and then repeat back to 1 again. Obviously this will work, right? Because it has to pass through all the colors if I just literally just put 1 to 2000 and cycle them around. Now this would give you k equals to 20,000. Because you have 20,000 regions, you can, let's say, just mark the first square of every region if you like. It doesn't matter where you mark it, to be honest. So this gives you 20,000, right? And of course, we will suspect, is this actually the best? But it gives us a starting point for how this may actually work out. For any two marked squares of the same color, any path connecting them must pass through squares of all the colors. Now, let's say that I've got fancy region shapes that are not just columns or rows, right? Maybe there's some cleverer way to do this. I would just sort of just put a schematic like this. So arrow means connected. This region can touch this region, which touches this region, and then I went from a square in region 1 until 2000 and back to 1 again, let's say. Right? So suppose that I've got this. Colors are just 1 to 2000 without any meaning. So of course, without log, this is fine. What I notice is quite interesting when I think about, okay, so 1 goes through all of these. Can the region 2 here connect to anything else? Now, obviously, it cannot connect to region 1. Because if it connected to region 1, then it would just have come like that, without going through the rest. Can it be region 2? Now, of course, 2 connected to 2 would just be region 2, so that doesn't make sense. And if it's anything else, all the rest of them could have come here. If it's not 1, it could have gone through here without going through 1. So if let's say this is 4, that means that 4 came to 4 without going through 1. So in other words, I cannot connect anything here at all. And the same logic applies for all of them. I cannot connect any of these here at all. So all my regions can only touch their two neighbors. And if we continue on, we can ask, well, what could I do? Well, I could extend the 1, right? And if I extended the 1, it can only be 2. Because anything else, I have basically allowed them to skip 2. So it must then be 2, 3, and repeating again. So therefore, the regions can only touch as this sequence of 1, 2, until let's say you reach 2000, then it repeats back to 1 and 2 and so on until eventually it reaches some k like that. So it just keeps on going that way. Now my last question is there some clever way that you can make a lot of regions? So can I get more than 20,000 regions? that are touching in this way. if you think about it, the answer doesn't feel like yes. And that's because there's not enough space, right? So I'm going to quantify that by saying, let's just say no, right? And consider, okay, let's say the regions go from 1 to k, right? Where I just call this thing 2001, 2002, and so on. Right? So 2001 has the color 1 again, 2002 has the color 2, and so on. So consider regions 1 and k, and the shortest path between them. Okay. So the shortest path between them has to go through everything, right? So if you draw a path from region 1 to region k, it must go through all of this by the reasoning that we have just said. It must have at least k squared, so all of these regions must be represented. But also, it is a 20,000 by 20,000 grid. Now, how far away can your squares be? If they are opposite corners, it still only takes 20,000 squares because of the grid size. So this means that k is at most 20,000, which is amazingly simple. But you have one last small thing to say, which is it possible that it loops back here? So that is one last detail we have to address. Can I have a loop? Because if I have a loop, then this argument doesn't work. The shortest path doesn't need to go through the whole thing if it's a loop, right? It can just leap from 1 to k. Remember we said you can only have 2 neighbors. Can it loop? Answer is no. So the loop is impossible. And the reason for the loop being impossible is that if you had this grid here, and just think about, let's say, can region 1 touch region 2 and region k without 2 and k touching each other? So 1 touches 2, 2 touches k, but these 2 are not supposed to touch each other. So the simple explanation is that if you draw any region 1, let's say in the middle of nowhere, then this portion around it has to be shared between k and 2. Now, how do you share it between k and 2 if they are supposed to not touch each other? Impossible, right? So therefore, the only way that this can work is that region 1 has to be able to separate its boundary into parts. If the boundary is not separated, then at some point it would transition from k to 2, and that's when they're touching. So the only way we can do is something like, let's say if region 1 is something like this, and region k is here, and region 2 is, let's say, somewhere here. But in that case, k and 2, there's only one path, or rather only paths between them that go through 1. Right? Because if they're only connected via 1, then this path here doesn't exist. The one that doesn't go through 1. So not connected via 3, 4, 5, etc. And that's a contradiction. So that's a small little detail. How many marks is something like this worth? I have no idea. But I think this question here is surprisingly the most intuitive one, where you don't need anything too technical. It's just really surprising that such a simple construction as, dividing it into rows is optimal. So as we can see, the last question is really not the hardest question, although we might argue that the first question is actually the easiest question. So before we go, just a few things. First of all, this is hard. This is still considered hard, so don't feel too bad regardless of how you did. Second of all, if you're taking the SMO Open Round 2 in a few days, all the best. And I think we should prepare for a difficult paper, seeing how the senior paper looked like. And of course, if you have any other suggestions as to how we might solve these questions more efficiently, please leave a comment below. And as always, like and subscribe for to be alerted for all the subsequent review videos that I may or may not be doing. So thanks everyone, and see you again soon.